learned about random variable. No. Probability space, right? The very excellent topic of probability space. Wait a moment. Why is this? Okay, now, as we learned, if probability is like a triplet. Okay, right? We learned many interesting things. We learned martingale, and we learned martingale, and we learned Doomb's martingale process, and we learned probability space. A probability space is a triplet with a sample space, and then sigma field, which is a family of event, family of subset of this probability space and of this probability measure, probability function. This is a function defined on this family of event, and it has this property. Functional value of null set is 0, entire set is 1, and sum of two probability of union of two disjoint set is the sum of the probability of each set. That is the definition of probability. Now let's define random variable. We have defined sigma field and random variable. Well, random variable is also kind of function. Okay. Now we define the sample space, right? Sample space, and then random variable is basically function from sample space to the real number. And then it has a positive, it has this kind of properties. So for any number, okay, any set, actually it doesn't have to be a number, but any subset possibly for any A in R, okay, in R. So A is a number like a 3 or 2. There is a corresponding element in sample space. So X, omega become A. And this set of omega should be in F, family of event. Okay, this is weird. So again, there is a function, so once you have image, you can find the domain. Okay, and that is in your sample space. No, sample space, not in your family of event, sigma field. From the sigma field. So intuitively speaking, our variable x is random variable. If for any possible outcome A, we will know whether x has this outcome from knowing the outcome of event in this one, in the family of event. This kind of random variable, in the mathematically speaking, x is a random variable if it is a called measurable function, 측정 가능. If it is this random variable measurable in the family of event. For example, let me give you example. Let me give you example. Suppose you roll the dice. Okay, you roll the dice. And you roll the dice, and then 전세 리포 컨트롤. Suppose if you roll the dice, okay? If you roll the dice, the possible outcome is 1, 2, 3, 5, 6, right? If you roll the dice, sample space is 1, 2, 3, 4, 6, right? And now let's define the family of event. Sigma field like okay, this is a family of event. If you look at this family of events, we have to check whether it is a sigma field or not. It is definitely sigma field because if this is here, its complement is entire set is here. Okay, let's go to sigma field. In order to become a family of event, it should satisfy. It should be sigma field. Sigma, if A is in F, A complement should be A. So this is A, is complement A. This is in here, is complement is null set also here. Okay, that's good. About this 135 odd number. If this one is here, what is the complement of odd numbers? It is 2, 4, 6. This is in the sigma field. This is in the F, and its complement of 2, 4, 6. This is also here. This is here. This is here. So this is sigma field. Okay, right? So this is sigma field. But if you look at this sigma field, this is interesting because your information is limited. Okay? Information is limited. Basically, this one is the event when something happened. You know, event, probability event. In the probability event means it is a subset of a sample space. The event, right? If you look at this kind of subset, null set, odd number, even number, well, there is no set such like 1, 2, 3, 4, 5, 6, right? So it means that if we have family of events like this, when you roll the dice, you don't have full information about the outcome of the rolling the dice. Okay? If you roll the dice, you don't know whether number is 1, 2, 6, or whatever. You only know whether it is odd number or even number. Someone else rolled the dice and she tells you, okay, we have now even number, or this time we have odd number, something like that. You cannot distinguish each number. Okay? So this is the kind of, so in this sigma field, we use in mathematics, sigma field is mathematical concept, and sigma field has wide application. In probability theory, we define probability in the sigma field, F. Sometimes it specifies information of how much information a people have, a person has. When we say amount of, when you specify amount of information someone has, we often use this sigma field. In this case, someone rolled the dice, we only know other even number. In the information set, null set, inside set is obviously there. We know someone rolled the dice or not. At least we know that. And then in addition, we know whether it is odd number, even number. Right? But we don't know, we don't have the refined information. So sigma field can be something like this. And then suppose let's define random variable like this one. Suppose this is random variable. Very simple random variable. If 1 happens, the value of this random variable 1. If 2 happens, the value of this random variable 2. Is it measurable? Meaning, is this random variable is the random variable in the probability space? It is clearly not, right? When in this kind of situation, we say this random variable is not measurable. Measurable. In Korean, it is 측정 가능한, 잴 수 없는, 측정 가능한. It is not measurable because in the random variable should be measurable, which means that when we have inverse image, where is it? We have an inverse image. Okay, like suppose let's say suppose x is 6. Then inverse image of 6 is 6, right? But 6 is not in the F, right? So this random variable, basically this random variable is not measurable with this sigma field. This random variable too refined, and we have too crude instrument. So this random variable is not measurable. Okay, obviously, right? We know only whether it is odd or even number. That's only information we have. But this random variable requires that when 1 happens, the value should be 1. 2 happens, the value of 2. This kind of random variable is not measurable. We cannot measure this random variable with our limited information. So this is not random variable. But this is random variable. Even number is 1, and odd number, okay, something like this. If even number, roll the dice, if even number happens, suppose some lady rolls the dice, and if it is number, you receive $100. And if it is odd number, now you give $100. So it is a betting, right? And odd number, even number, you give $100, you receive $100. In odd number, you have to give $100. Okay? So again, it is random variable, right? It is exactly, this is measurable function. Because suppose now you have the $100. What is the inverse of $100? It is even number, so it is 246. 246 is in F. So it is measurable. Suppose you now, even number, now you have to give minus $100. So what is the inverse image of giving minus $100? This is 135. This is again subset of element of F. So it is measurable. This is measurable. Okay? So again, the random variable is for the random variable function, and a function becomes random variable if it is measurable. Measurable given our information set. If this function is measurable, we can measure somehow that function with our information set. Meaning that when there is outcome, value of a random variable, we can find the inverse of that value. And if that inverse is in the family of event or sigma field, if the inverse forms sigma field, then we can say that it's a random variable or measurable function mathematically. So random variable is a special kind of measurable function in mathematics. Right? So this is an exact, rigorous definition of a random variable. I know you all learned what you mean. You all heard of random variable, or your statistics class or econometrics class. I know you learned random variable, but I don't think you have ever learned exact definition of random variable. And this is the exact definition of random variable. And I think it is important to know exact definition of random variable. 확률 변수. Any question? Actually, so let's come to this one, okay? Let's come to this one. In this case, well, this x is not measurable. Again, this one. If we have this kind of information set, we know this is not measurable, right? This is not measurable. So let me give more interesting example. Now suppose we have a sample space. Sample space, let's say it is like this. W and W belongs to 0, 1. Okay. So it is a set of is a real number between 0 and 1. Something like that. Okay. It is a real number. Okay, 0 and 1. So suppose this is real 9, 1, 0, and they are real number, right? So now we have in the previous case, it is a discrete. Now it is continuous. Okay. Now let's say our family of event looks like null set and the entire set, and say and the 1/2. And then 1/2 and 1. Okay. This is again sigma field. Okay. Now it is like it is something like you spin a wheel. Okay. You spin a wheel and spin a wheel and you throw dot. Right. And then it is basically random variable. In this case, the event is location of your dot, possibly, like distance from the how can I say? Yeah, something like that. You know what I'm saying, right? Dot is like drawing a dot, and the location of dot from the original starting point, or possibly it is like location of the needle in the watch, something like that, in the prime. Something like this. And then now say random variable is something like this. Okay. Again, this random variable is not measurable, right? This is not random variable. This function is not random variable because this function is not measurable with this crude information set. We know we drew the die, and we know only whether the dot is this half or that half. Only we know that. We don't know exact location of the dot, something like that. Okay, so in this case, again, is another example that this is not measurable. Okay, not measurable. But this function is measurable, right? Let's say this is A and B, and when A happens, the value is $100, and when this happens, it is minus $100. When you throw dart, the dart is one half, left half of this wheel, you receive $100, and the other half you have to give minus $100. This is a measurable function, and this is a random variable, right? So even in this case, but we can define this one. Okay. Suppose now we have random variable this one, but now we can define this one. What do we usually say this kind of thing? This is kind of thing is called conditional expectation. Okay, it is called conditional 조건부 기대값, right? It is conditional expectation, but we can calculate this one. So we don't know. This is not measurable. This is not measurable. Therefore, we don't know the value of this one because we have only limited information set. But given this information set, we can guess what is x. Okay, we can get the conditional expectation of x. So basically, this conditional expectation, this thing is measurable function, right? So this is, once we define this conditional expectation, then this conditional expectation is random variable. Right? Let me explain why. Suppose we want to calculate conditional expectation with respect to this one. Then when we calculate conditional expectation, now, okay, we want to estimate x with conditional on our information. Okay, and in our information, we don't know exact location of dart. We don't know exact value of x, but we know whether it is the first half at least, whether it is the first half or second half, right? Given our information, we don't know exact value, but we know whether it is this area or this area. That is at least we know, right? Because this is our information set. Do you know what I'm saying? 무슨 말인지 알겠어요? Right? So again, we don't know exact value, but given our information, given this information structure or sigma field or family of event, we know whether event is first half or second half. Okay. So therefore, in this conditional expectation, let's say this is A and B. Okay. When A happens, when A occurs, when A occurs, right? A occurs, or it means mathematically when event, when element is expanded, when element in the subset of A, it belongs to A. Okay, then okay, when A occurs, then we can calculate conditional expectation such that when A happens or when element is between 0 and 1/2, we want to calculate conditional expectation of x, which is obviously 1/4, right? Right? Because we know in our information, we know whether this one occurs or this one occurs. Suppose this one happens. So event is between 0 and 1/2. Now, whatever happens, the value of this one is exactly that one. So conditional expectation that some event happens between this and this area, the conditional expectation should be exactly half, right? You can do the integration, right? You can do integration 1/2 and this x dx, right? Integration. And the probability distribution in this case is 1, uniform distribution, so it is 1/4, right? Then 1/2 is 1/4. So 1/4. And then suppose B occurs. B occurs 1/2 and second half. And in this case, what is the expected value of this one? In this case, what is the conditional expectation when we know event B happens? What is that? What is the conditional expectation? What is exactly half of this one? It is 3/4, right? Right? Again, this is 0, 1/2, and exactly half of this one is 1/4, right? So when A happens, we know conditional expectation 1/4, and this is 1/4. And this is by definition, almost by definition, this is therefore conditional expectation, random variable. Because when 1/4 happens, we know its inverse image is A, which is sigma field, which belongs to F. When this 3/4 happens, again, 3/4 happens, this inverse image is 2/4, 2/4 belongs to F. Therefore, conditional expectation given this information set is random variable, measurable to this set. I think this is enough for today, and see you next Wednesday. If it is not fun, I will not discuss this probability thing anymore and go to derivative and those things. If it is not fun, I'll think about this one. I think you are not that interested in. I can see your eyes, and most of you seem quite uninterested on this kind of mathematical discussion of probability. Therefore, I'll think about changing the topic to the more real, more practical ones. Okay, anyway, see you next week.